Okay, so I'm going to talk a little bit about autoregressive models for geophysical flows. This is largely going to be data-driven autoregressive models, and then some perspectives on analyzing these models theoretically, somewhat physically, and some ideas of deep learning theory as well. I'd like to give a shout out to some of my collaborators across industry and academia who were instrumental in developing some of the models that I'd be talking about today. Some of this work was done early on with folks at NVIDIA and Lawrence Berkeley Lab, and more recently with folks at Argonne and UChicago. Okay, so we begin with this new paradigm of weather forecasting that have emerged in the last few years, particularly in terms of short-term weather, where we saw that there was an influx of machine learning models, purely data-driven, with little to no physics inside these models that were able to do reasonably well for for outputting the prognostic variables that you typically deal with in a numerical weather prediction model. And the earliest one amongst them was something that we released back in 2022 with folks from Berkeley and NVIDIA called ForecastNet, where we came very close to IFS scale forecast accuracy, but not quite. And since then, there have been many new papers, folks from Hawaii, China, and then Google DeepMind, who released these very expensive, very large weather models that are extremely cheap to run in inference, which means that if we were to do weather prediction today with any of these AI weather models, the amount of computing resources that you'd need is typically a few thousand orders less than what you typically use on a supercomputer. And by a few thousand, I mean in the ranges of 100,000 orders cheaper than what you would typically do with a numerical weather prediction model. And the highlight for these models are the fact that they're actually able to reach accuracies that are far better than the best numerical weather prediction models out there. And by the best, I mean the CMWF's IFS and the ensembled version of IFS. So for example, here's a little schematic, well, not so much a schematic, but an emulation of a weather forecast with two of these really great models. One is called Pangu Weather. It's not important what these models are. It's one of the many very large deep learning architectures. What is important to note that is these models do not have any physics inside them, except for the fact that they're trained for over 40 years of reanalysis data that we have. The models actually have no physics incorporated inside them. And then if you look at the accuracy of these models and see how they perform, not just on some statistical metrics, but really looking at metrics that typical meteorologists would look like, you'd see that they're doing far better than what numerical weather prediction models do, and at a far lesser cost. And by far, it basically means at zero cost if you compare it with actually running a numerical weather prediction model. In terms of predicting extreme weather, they actually do a pretty good job, and again outperform NWPs. So it was significant improvement over what we had maybe 4 or 5 years ago, when a whole bunch of folks were getting into machine learning, trying to do weather forecasts or similar sort of things in this field. Things have really moved since then, and we now have models that really are operational to the extent that ECMWF has operational AI models that consistently outperform their numerical weather baselines. So these were weather timescales. So as soon as you have models as cheap as these, which can really run on a few GPUs in a few seconds, and give you the forecast that you're looking for. Also, generally the amount of expertise that it takes to actually run these models are far less as compared to compiling an NWP code on whatever supercomputing architecture that you're interested in. So generally there was this interest in seeing how these models are actually performing for longer timescales, and this is the basis of the premise of this talk. Is despite the fact that these models have such great accuracy at weather timescales, one of the central questions that we wanted to ask was, okay, given that they don't actually have any physics, sort of de facto physics incorporated inside these model details, do they actually preserve physics, or do they look anything close to what a physical model would look like? And one way to test that is to actually run this model for a long period of time, and then see whether any of them preserve sort of kind of long-term dynamics that you would expect from any numerical model. And the way to do that would be like train on high-resolution simulations with different forcings, produce long synthetic data sets, and then do what every other climate scientist do, is look at the internal variability that they're producing, see whether how well you capture your uncertainty, whether you can capture your extreme events, and then try to define metrics for physically consistent systems. And that's difficult to do. That's obviously much easier to do when you're dealing with language models that are typically more popular in the ML community, where you can look at the text that they're outputting and you know whether it's right or wrong. But for physics, it might actually be a little more difficult, and it may require some analysis. So that's the premise of this talk, is how physical are these models that without a doubt, and there's no catch here, without a doubt, are definitely superior to numerical weather prediction models at a much lower cost. So giving an impression of free lunch in this case. And the general approach to training any of these models, and one thing you'd see is that throughout the length of the talk, I wouldn't really worry about the specifics of the ML architecture, because some of the issues and the solutions that I provide are typically agnostic of architecture, as it should be. And the way these models are trained is that you're trying to solve a discrete dynamical system, and for weather and climate, the state of X in this case, the prognostic variables can go up to 1 million or even more. So it's a very high dimensional nonlinear dynamical system, it exhibits turbulence and everything, and it's also a multi-scale, multi-physics system, right? So it's not just solving 2D not just solving Navier-Stokes equations, but a little more than that. There are several levels of physics that you either capture or you don't, and you parametrize. So it's generally a high-dimensional coupled system that you're trying to solve. And the way ML approaches this problem is rather simply is that if you have historical data, let's just replace the right-hand side of this discrete system with your favorite neural architecture. And this is where things become a little hand-wavy and a little complicated as well, is that it's hard to say what's the best N, and for a good reason, is that it has been shown, or it has been seen so far, is that the bigger the N is, and by bigger I mean larger number of learnable parameters, the better it works. And then there are these unique N's where you put some physics in or you don't, and like so far the state of the art doesn't actually have anything remotely resembling physics inside these architectures. But you have these little bells and whistles on top of N, and sometimes these work and sometimes it doesn't. And there are all these like names out there, like vision transformers, neural operators, and so on and so forth. And this is not just for the climate or the weather or generally the geophysical fluid dynamics community. It's for any of the natural sciences where everybody thinks that their data is unique. So there are obviously idiosyncrasies that go into building these neural networks. So there's generally an absence of theory, something that has not been the case when you develop physics-based models. Your numerical models are very grounded. They're grounded in mathematics and they're grounded in theory, and the kind of theory that involves proofs and convergence bounds and all of that. The N's that have done so well in this context have none of that. It doesn't have any theory. It's very hand-wavy. It's mostly like, let's put as big an N as you can, and then see how well you do. And then there's a question about what delta t makes most sense. And if you're a numerical analyst, you'd say, well, you want to write a really good numerical model, you choose a small delta t. And how small the delta t is kind of governed by your CFL condition, or more broadly, how much compute you can afford. In this case, it's kind of the opposite. The larger the delta t is, the better the model forecasts are, which absolutely doesn't make sense to a mathematician, but empirically that is what seems to work. So the questions that we could try to ask, and probably you can't see it unless I move this up. And the questions that we are trying to ask is whether we can build principal structures in N, and by principal structures it would not assume what the actual underlying shape of N is, or the architecture of N is, whether it's a big deep neural network or a big vision transformer or a neural operator or something like GPT, but rather there are certain structures we can build inside N so that the behavior of these models become very predictable, and we can do the kind of theory that we're used to doing as numerical analysts writing CFD code or climate models generally. So what we did recently was that we took some of these AI weather models, some of the best out there, the ones that actually consistently, very comfortably outperform numerical weather prediction models, the ones that are used to generate forecasts every day for the past 50 years. And we compared it, and so we sort of ran it for longer periods of time, and we tried to see how these models behave. And we kind of saw that there are two ways these models become really bad if you run it for a while, beyond sort of weekly timescales. Is that they either become unstable, which is not necessarily a bad thing, because then okay, this model is good for 15 days of prediction or 10 days of prediction, and after that it's not, and there's no reason why any of these models should be stable for a long period of time, because there was no stability analysis that went into it, or nothing actually that's preventing them from being unstable. But there's another class of models, and the Pangu weather model was one of them, is where they don't go unstable, they give you bounded predictions, but they're physically inconsistent. And how do we say physically inconsistent? It might be super simple, where you see wind start moving in the other direction in the northern hemisphere, and well, then this model is completely bad. Or it might be a little more subtle, where it's hard to say whether any of these Z500 lines, the shading is Z500, and then we have the shading is Z500, and then you have U250 contours sort of overlaid on top of them. It's hard to say whether it's right or wrong, whether it's meaningful or not. But then, if you look at the climatologies obtained from these runs, this is a stationary climate. There's no climate change. Well, there's no enforced radiative forcing here. And if you look at sort of the mean, the zonal and the time mean of some of these variables, like geopotential or sort of wind velocities at 250 hectopascals, what you would notice is that the climatologies are terribly off. They're terribly off towards the poles, and sometimes they're really off near the equator as well. For example, the Pangu 24-hour model, which is one of the best AI models out there in terms of short-term forecast, show 20 meter per second wind speed at the equator, which is completely unphysical and has no correspondence to reality whatsoever. So these analyses can be a little nuanced, because you actually have to go a little further than visually inspecting them. But then you realize that there's a bunch of problems with these models, and people need to figure out what's going on. And one of the basic problems with these models is something called spectral bias, where even for the first time step of prediction, if you look at the power spectrum of these models, none of them match the true power spectrum of the system. So they don't actually match the true power spectrum of the observed data set, even at the first time step of prediction. Basically, they only capture synoptic timescales, which is why they get away with weather timescale forecasts. And after that, they go haywire. They either show excessive diffusion, or they become unstable, in a way that if this was inverse cascade, you'd see that the large scale is growing upward. So this is the fundamental problem. And this is true for any AI model, really. Any deep neural network, no matter what the architecture is going to have these problems. And to explain that a little bit further, we need to look at how these models are trained. They replace the right-hand side with some neural net, and they optimize this L2 loss function. If you think about it carefully, the L2 loss function is basically just a low-pass filter. So if you train this model, for example, what we did was we took one of these models, these really good ones. It's not important, again, what that model is, but one of the good ones, and we trained it on a very simple two-layered quasi-geostrophic flow, where we know the whole dynamics. It's not as high-dimensional. There's no coupled ocean atmosphere or any of that stuff here. It's really just 2D Navier-Stokes equations. And you look at the first time step of predictions, and you'd see that it doesn't capture about half of the wave numbers. And the reason why it doesn't capture half of the wave numbers can be derived really on pen and paper. If you look at the loss function at its gradients, do Parsifal's decomposition, you'd realize that the whole training process is governed by updating the weights of the model, which are given by thetas, with this gradient step. And this gradient becomes smaller and smaller as your wave number increases. So basically, once you learn about half the wave numbers in a decaying spectrum, then the rest of the wave numbers contribute very little to this term, which is basically the difference between the reference spectrum and the predicted spectrum after it has captured about k of these wave numbers. This term is very small. This term decays exponentially with k. So essentially, this gradient step does no updating. So the learning stops as soon as you learn the large wave numbers. And this is true for cats and dogs. Like when you train big models on cats and dogs, the same thing happens, because this has nothing to do with the architecture or the data. In fact, it has nothing to do with turbulence, really. It has just got to do with the fact that the spectrum is decaying, so this quantity is very small. So there's no way you would learn this part. And you can kind of, derive how these models would behave for different activation functions, based on this gradient step. So one way to fix it is to actually have a regularizer in Fourier space, where you instead of forcing this model to learn the prognostic variables in physical space, you actually force it to learn in the Fourier space, because that's where it goes wrong. So that's where it goes wrong. So basically, you have a regularization in terms of its Fourier spectrum after a cutoff wave number, this K threshold in this case, and you add that term as a penalty with a Lagrange multiplier, so that you force the loss function to move in a direction such that mu theta also decreases along with this low pass filter, which is the RMSE loss. The other thing to do, the other principal structure that you can incorporate into this model is something that we've been doing for a long time, is just a time integrator, except you have to do it a little cleverly, wherein instead of replacing the entire right hand side with a big giant model, you replace only the residue with that big giant model that you don't understand, but then actually have an explicit time integration step that kind of performs higher order integration. So for example, if you were to do like a simple Euler step, you'd have an identity matrix as the H operator. If you had something like RK4, you would write a custom differentiable layer, so you can back propagate errors through this layer, but then it actually performs fourth order integration. Similarly, you can do implicit time stepping with these models, where you basically have an implicit layer in each forward pass. You use a fixed point iteration to solve for the thetas such that you preserve the xt plus delta t. So these are sort of the principal structures that we're talking about. Is that you have things in Fourier space that actually preserves the spectrum, and you have an integration that preserves the order of integration when you move forward as an autoregressive model. So when you do this, and we tested this out on a bunch of different systems, and I talk about each of these different systems. We tested out a two-layered quasi-geostrophic model. Again, this is hardly weather or climate. It's just a model representation of the mid-latitude dynamics. But you know the whole system, and these state-of-the-art models have a hard time remaining stable on this model as well. So you do this and you run this for 300,000 days of integration. You see that you get the invariance correctly. For example, the time and zonal mean, and this model with this Fourier sort of regularization and this RK4 integrator, we call it forks in this case, it remains stable for about 300,000 days. So it will remain stable forever. It gets the right variability of the system, and it gets the right spectrum. Your spectrum stops deviating. It kind of remains the same as that of the true spectrum. In a stationary system, your spectrum is not supposed to move, and that's what you're trying to preserve. And these fixes are sort of agnostic to the architecture. It doesn't matter what architecture you have underneath, because that kind of depends on the amount of computing resources that you have. So we try to scale up this theory on bigger models that are trained on real weather data. So ERA 5 is ECMWF's reanalysis data, where we trained a model on 40 years of reanalysis, 30 years of reanalysis, then we initialized it and let it run for another 10 years, and we computed the climatology. So really having these two simple fixes is going to ensure that you're integrating the model in a sort of principled fashion, and you preserve the long-term invariance. So here you see the zonal time mean of our predicted forks, which is given by this line on top of ERA 5. While, as you can see, the other state-of-the-art models, as I had shown, would deviate from the climatologies, and similarly, the spectrum would get preserved as well. And we decided to see whether sort of the same things would work in the ocean, because if we were to do climate change at some point with these emulators, we would need to be able to couple these atmospheric models with ocean simulations. And this is an example of again, an ocean model, a fully deep learning based ocean model. And by deep learning based, it means that it's some neural architecture. Again, not important what the architecture is, but it has these two criteria where it learns things in the Fourier spectrum in a way that it ensures that the small scales are preserved, and then it does temporal integration in the same fashion that we do temporal integration in PDEs. It preserves sort of the order of integration when you're moving forward in time. And you can see that this model remains sort of stable and gets the right eddy shedding event. So we trained this on observations over the Gulf of Mexico and North Atlantic, and sort of did a whole bunch of analysis and how well it captures the dynamics as compared to the observations, and put a link to the papers if you're more interested in it. So based on this, we decided to see whether we can get some of these models to work as a climate model. This is something that we released a couple of days ago. It's called Lucy, stands for a lightweight uncoupled climate emulator. It's uncoupled because there's no ocean here, and we're basically trying to couple it with OceanNet. It's low resolution, has minimal HPC infrastructure, and the reason I highlight this is that most of the state-of-the-art AI weather models are coming from big tech, NVIDIA, Google, and so on, and the amount of compute infrastructure that you need to train this model is just ginormous. It's quite impossible to kind of rival that staying in academia. So one of the things we want to do is how much can we do exploration and science if we were to use some of these models, and the answer is none, because we can't train any of those models. So we wanted to release this very low resolution, minimal HPC requirement climate emulator. It requires about 2.5 hours of training on a single A100 GPU, and you could produce like 1,000 ensembles of climate emulation. So what we did, again, it has sort of the same bells and whistles that I was talking about. It has this uses something called a spherical Fourier neural operator, which computes the loss function in Fourier space using the spherical harmonic transform, and tries to ensure that the spectrum is sort of captured in the small scales as well. And we have the incident solar radiation as a temporal embedding, so that we can unroll these forecasts for several hundreds and thousands of years, and then really investigate how well we have captured the variability or generally the dynamics as we move forward in time. This is a Hofmöller diagram of temperature. This is near surface temperature, because this entire model is trained on the sigma levels and on a Gaussian grid, and you see that you get the annual cycle of temperature very accurately. This model does not impose SSTs or any of that stuff. It's really just a standalone atmospheric emulator. Gets the annual cycle of temperature. This is how some of these videos, some of the emulation looks like. There's no inconsistency when you unroll these videos. And then we looked at the long-time climatology.
Can you wrap up?
Sure, great. And then you look at some of the long-time climatologies, and you see that the zonal, the temporal mean of the zonal mean time mean of the temperature is accurate, and this is how the biases would look like. So I'm going to end my presentation here, and I guess if I have a couple of minutes, then I'd be open to take questions.
Thank you, Ashesh. Questions?
Yeah, hello. Thanks for the talk. I have one question. The last part, the climate change. Actually, you have no data for the climate change to train your model. So what is the reason you do this, the last part? I can understand the weather prediction. That's a beautiful example for machine learning, but climate change?
Sure. Okay. So we don't have observational data, obviously, for 100-year runs, but we can run, for example, E3SM simulations with different radiative forcings. So why do we want to do climate emulation in this case? So for a couple of reasons, and one of them, without climate change, without even considering the entire problem of climate change, is that we can first try to narrow down the uncertainty of extreme events that have return periods larger than the observation records. So if you have return periods of extreme events that are larger than 40 years, that are longer than 40 years, and if I'm able to run 1,000 ensembles of these emulations for longer than 40 years, we might be able to narrow down the uncertainty of the return period of these extreme events, so sort of gray swan-like events. So this is without climate change. The reason why I kept talking about climate change is because one of the other reasons we wanted to build this emulator was to sort of do the following experiments. So if you train these models on, say, different radiative forcings, so by training this model on different radiative forcings, I mean, say you run E3SM simulations with different radiative forcings, and you train these emulators on a set of these long runs with different radiative forcings. Then you'd want your model, and then I'd want my emulator to basically tell me what the dynamics would look like for a new radiative forcing. And this, and if you can effectively do this, we would be able to do things like look at the response of the system to heating and things like that. So basically, all the things that we've been doing with linear response theory becomes a lot more tractable if you have these very nonlinear emulators that are able to incorporate forcing inside them. So you can see how, for example, things like circulation would change over like a 100-year period or like a 10-year period if, for example, you have equatorial heating that increases. Or for example, if I had SST in this model, if I increase the bias of SST, how would the response to the atmosphere would be to that bias in the SST? So this is the reason I brought up climate change, not because we have, there's no observed data obviously, but because we could do response projections using these emulators more efficiently without the linearity assumption, if that makes sense.
I have a question. I'm not sure it will make a lot of sense, but for the two-layer QG model, you just sort of fixed it by adjusting the cost function. I'm not sure that's the right terminology, but I'm wondering if you could just train a separate neural network to fix the error. Like you propagate it, there's an error, and then train a separate network to sort of get the error and proceed that way.
Yeah, absolutely. We could totally do that. The only thing to keep in mind in that case is that you're going to predict, for example, a physical variable with two different neural networks that are uncoupled with each other. So we have to ensure that the conservation laws in this case would not be violated, because one neural network is not talking to the other. So you're basically, for example, predicting one part of the velocity with the neural network and then correcting the remaining part with another neural network. So the final added velocity should reflect the right energy. But what you're saying is absolutely right. Lorzana, for example, does a lot of model error correction with an approach similar to this, where they have a low resolution numerical model and they correct the error with a neural network.
All right, thank you, Ashesh.